Hey folks, it's John Frensley with World's Finest Physics, and I'm going to show you a lab I do that involves both the Impulse-Momentum Theorem and the Work-Energy Theorem. So if you'll look here, I've got my document camera, and I'm kind of using it to show the lab setup here. So what you'll see here is a Vernier motion sensor, right? All right, here's the USB cord. It's going to plug in my laptop. And then if I come along the other side here, I've got the Vernier force sensor here, and it's got its little cords leading to my computer also. It's got its little hook out. It's attached to one of these post bar rod type things that come with the Pasco setup, actually. And then underneath you see a Pasco track. See the Pasco track there and a little barrier. And here you'll see my little red car, and it's got another post on it as well. I'm going to put on there 4 of these Pasco bar masses or something like it, right? Okay, so you see the Pasco right there. And then I've got my scale I'm going to use to measure the mass. And then the important part is one of these little badge holders here. Let's see if I can focus this at all since yeah, that might be a little bit better. Okay, so one of these here badge holders, you see? So the badge holder doesn't obey Hooke's law. It actually, I don't understand how it does it, but it pretty much exerts a constant force. It's not perfectly constant. So here's what I'm going to do is I'm going to put my nifty car on here, right? Okay. And then I'm going to put the badge holder. I'm going to open up the little badge holder piece like that. Maybe I'll bring it a little closer to the camera so you can see this. So there we go. I'm going to put around this little post, screw the post in a little bit better. I'm going to snap that little bad boy there. This is just from Dollar Tree. They sell them 3 in a pack for $1.25 nowadays. And then let's get over here where you're going to see how I'm going to attach this. Hopefully you can see how I attach it. I'm very simply just going to hook that around there. So you see I just hooked that around there. Now before I hook that around, I had to zero out the force sensor, right? You always got to zero out these Vernier force sensors. All right, put that on there. All right, I'm going to pull this back, right? Pretty much until, oops, you don't want this little spring piece out, because the motion detector over here is going to get confused when it doesn't see the flat end of the car. So let's get that spring piece in there. Right, let's get it in there. Okay, so what am I going to do? I'm going to pull it back until I feel like the cord is fully stretched out. All right, so there's the motion detector. All right, and there's the force sensor. All right, so I'm going to start taking data. I can't record this and take data at the same time, so I want you to pretend like I push the button, right, the sound that the motion detector makes. So I'm going to let go. I'm going to catch it at the other end so it doesn't smash into the force sensor and damage my force sensor or break the little badge holder, right? I don't want to do that. So here's what it looked like when I ran it once. So what you'll see, first of all, nothing as I was waiting to hear the clickety-click sound. Then we see, this is the position graph down here. So you see the acceleration happening. It's parabola. And then it stops and even bounces back a little bit. And that was because I had to catch it. So you see that here on this force right here, okay? Well, I'm not interested in position versus time. I'm actually interested in velocity versus time. So let's look at velocity versus time. So nothing until I begin to speed up. I'm going to ignore all the data before this moment, 1.5, only because I want to make sure that the car is definitely moving before I start considering the data. And I'm going to stop caring about data here at the highest peak. It's 2.45 seconds. I'm going to just go one before that, just because, I'm worried about other forces being involved when I catch the car, whatever kind of thing. So I'm only going to take data between 1.5 and 2.4. So that's a few points after we're clearly moving, and maybe a point or two before you reach your highest point. So what graphs do I care about? I care about these 3 graphs. Velocity versus time, you see down here. Force versus time, you see up here. And then I also care about force versus position. Those are the 3 graphs I care about: force and time, force and position, and velocity and time. We know force and position going to get us work. Force and time going to get us impulse. And then the velocity and time is going to get us both change in kinetic energy and change in momentum. Now, here's my problem with Vernier graphical analysis. There's no easy way that I know of. Maybe you can shout at me in the comments how I can actually take this and just straight up delete, like pushing the delete key doesn't make it go away, right? in where I come from, you push delete and it goes away, right? But that's not the case here. And then the same thing here. I can take it, I push delete, push backspace, and it doesn't go away. And I know that in old versions of Logger Pro, you could like cross out data points, right? You can't get rid of them. You can cross them out. It's not happening here, right? So here's what I did. I know that there's a way to do it, but Vernier is not user friendly. So I started at the 1.5 time, and I went to, okay, you see how difficult that is? Very difficult to use. And I went to 2.4, and I just literally just copy pasted this data into this Excel document right here. So I've got my Excel document right here, okay? There's the mass of the car. I got it from the scale, right? What about the time, Friendly? It's not 1.5. It's not 1.55. It's not 1.6. Yes, because I took that first time, 1.5, and I subtracted it from all of them so that it would do a horizontal shift of the graph back to 0. So rather than having a few data points over here and all this blank space so I could get up to 1.5, I shifted all the data points back. Same for position. The first position was 0.256. So I subtracted 0.25 from every position. So it starts at 0.006 for position, right? So I'm kind of trying to zero out the positions in time. So the position is really displacement rather than position, strictly speaking, right? So I created 3 graphs: force versus time, force versus position, and velocity versus time. So I know that Logger Pro Vernier Graphical Analysis can do a really great job of taking the exact area here. You could teach your students how to take the area. You just make a trapezoid, and then you just make another trapezoid, another trapezoid. Heck, I'll do it right now. Okay, so watch. I'm going to take the area of this force versus time graph. How do you do a trapezoid? Okay, a trapezoid is 1/2, look at what I'm doing, times the average of these two heights. That's you, and you. Okay, that's the average of the two heights times the width of the base, which is that minus that. Okay, are you looking carefully here? We have 1/2, the difference in the two forces times the delta base. So that's the area of just this trapezoid right here. So if I go down, 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 one less data point than these, right? So how many data points is this? Okay, that's 19 rows. So I'm going to do one less than that. I'm going to go down 18. I push Control D for down. And now that's the area of all these little trapezoids. And the area that I get, if I move down here, or the total is 0.95. Now, that's the area, splitting this into little trapezoids. However, what I did over here, when I said impulse right here, I just did a best fit line here, and I did one big trapezoid using the best fit line. So you see the initial force, that's the best fit line, not this data point. The final force, that's the best fit line, not the data point. And the delta T between the two, and I made a big, whatever you want to call it, one big trapezoid. So what was my delta momentum? That is mv initial and mv final subtracted. So I did mv final minus mv initial. I got the scale. What's v initial? Literally this first. That first. Just take that first one, right? Simple. Then this final one. Very simple. Take the final one. And then your delta P, you can even see the formula right here. Do you see it right there? There's the mass times final minus initial velocity. Mass times final minus initial velocity. So my delta momentum was 0.95. My impulse was 0.97. So 95 cents versus 97 cents. But that was treating one big trapezoid. If I made little trapezoids and did a trapezoidal rule, you gotta ask yourself, are your students in calculus? Should they be able to do a trapezoidal rule? Or do you know how to figure out, can you get graphical analysis to take the area for you? That was also 0.95. Look down there, it says 0.9. So 0.9515 versus 0.9502. That's pretty dang close. So I just showed that change in momentum, MV final minus MV initial, and impulse, the area under force and time graph, are pretty much the same thing. Now let's come over to the work energy part of this. So again, force versus position, I fit a best fit line there. And I did a trapezoid. Again, if you look here, it says the force at time equals 0. That's from the best fit line, not the data point. The force at time final, that's the best fit line, not the data point. Maybe it should say x equals 0 and x equals x final, whatever. The delta x was literally the subtraction of the final and the initial position. I literally just subtracted the two. Just subtract, that's the delta x. And I did, if you look at my work here, it's 1/2 times the average initial and final force times the width of the base. So it's like one big trapezoid. So I got here, I got 0.41 for the work. That's my area using one big trapezoid. Here I got 0.42 joules. So 42 cents versus 41 cents. Again, I think I'm doing a pretty good job. However, if you want to wait a second, and I will change this to the area of the force and time graph. So you see what I did? I just changed the delta t to delta x by changing from the A column to the C column. I'm going to control D that down. I'm going to look at the sum, 0.417 and 417 versus 421. 415, it's about the same thing. So you got to decide for yourself. First of all, how this is going to require at least the force and motion sensors. And then are you going to have your student do this by hand, by Excel? Are they going to do a best fit line in one big trapezoid? Are they going to do a little trapezoidal rule? You got to decide what you want your students to do. But I think it's a pretty good little lab that in one class period, maybe even less, you can get you can show the impulse momentum theorem, you can show evidence, and you can show evidence of the work energy theorem. All right, world's finest physics. You see my logo. Search us up on Google. Make sure you spell the word finest the way that it appears here, and you can contact me that way. And if you have any other questions, I'll see what I can answer for you. Bye.